Welcome to this work presentation on Multi-Modal Deep Embedded Clustering MM-DEC, a novel framework for mineral detection using hyperspectral imagery. Let's begin. Hyperspectral imaging captures how sunlight interacts with the Earth's surface and atmosphere. As light passes through scattering and absorption by dust, aerosols, water vapor, and clouds, they alter the spectral signals, introducing noise. Different materials reflect unique wavelengths, creating spectral signatures for vegetation, minerals, and water bodies. The EO-1 Hyperion sensor is a passive sensor capturing this reflected light, making atmospheric correction absolute essential for accuracy. To understand how hyperspectral imaging works, we must first explore the electromagnetic spectrum. The electromagnetic spectrum consists of different types of radiation, ranging from high-energy gamma rays to low-energy microwaves. Each type of radiation is characterized by its wavelength and frequency. Our eyes can, however, perceive in a very tiny region of the spectrum known as the visible region, which spans wavelength from approximately 400 nanometers to 700 nanometers. However, hyperspectral sensors can capture data beyond this range, including ultraviolet region, infrared region, and short-wave infrared region, providing rich spectral details that are invisible to the naked eye. Just like human fingerprints are unique, every material has a distinct spectral signature. By analyzing these spectral curves, we can differentiate between vegetation, water, soil, minerals, and other such surface materials. This property is the foundation of mineral detection using hyperspectral imagery. Now let's explore our proposed framework for mineral detection using hyperspectral imagery. Our workflow begins with data acquisition from the EO-1 Hyperion sensor, which captures hyperspectral data over our region of interest, Kiriburu, India. The acquired dataset consists of high-dimensional spectral bands stored in HSI.HDR format, which requires extensive preprocessing before analysis. Since hyperspectral data contains hundreds of bands, dimensionality reduction techniques are applied to retain essential spectral information while eliminating redundancy, improving computational efficiency. The process data is classified to distinguish between different land cover types such as vegetation, water bodies, soil, ensuring that only relevant geological surfaces are considered for mineral detection. Using pixel purity index, we extract the most spectrally distinct pixel, which serve as the reliable indicators of specific minerals in the study area. The spectral characteristics of pure pixels are matched with the known mineral spectral signatures from spectral libraries to detect hematite, a key iron-bearing mineral. Finally, the detected mineral regions are validated using similarity score and performance score of the clustering. This structured approach allows us to systematically identify mineral deposits leveraging hyperspectral imaging and machine learning techniques. Kiriburu was selected due to its popularity on iron ore deposits, making it an ideal candidate for evaluating our approach. However, a key challenge here is the lack of ground truth data, which makes accurate mineral identification a complex problem. To acquire the data, we use the USGS Globus platform, which provides free access to hyperspectral imagery. We specifically selected Hyperion data for its rich spectral resolution. Data preparation. Raw hyperspectral data is affected by atmospheric interference, sensor noise, and bandbands. Preprocessing is essential to remove these distortions before further analysis. We identify bands with extremely low signal-to-noise ratio and remove them from the dataset. These are the bad bands. They refer to the spectral regions where the data is highly noisy due to atmospheric absorption. These bands must be removed to ensure accurate analysis. Destriping is another crucial pre-processing step in hyperspectral imaging that corrects inconsistencies caused by sensor variations. These inconsistencies appear as vertical striping artifacts as seen in the first and second images, which degrade both the visual and spectral quality of the data. The third image demonstrates the effectiveness of destriping, where vertical striping artifacts are significantly reduced, leading to a cleaner and more uniform dataset. This enhances the accuracy of mineral detection by ensuring that the spectral features are free from sensor-induced distortions. In hyperspectral imaging, noise can have significantly degradation to the quality of spectral information, impacting mineral detection accuracy. We explored various statistical and machine learning techniques for denoising, and among them, the most effective were the denoising autoencoders, which improved the peak signal to noise ratio from 14 decibel to 44 decibels. Let's understand how this process worked. Denoising autoencoder. The input consists of hyperspectral bands. We have demonstrated here band 1 shown on the left, which contains useful spectral information. However, noise due to sensor interference, atmospheric scattering, and thermal effects corrupts the data. The encoder compresses the high-dimensional noisy hyperspectral data into a lower-dimensional latent space while preserving key spectral patterns. This step filters out unwanted noise while maintaining critical mineral-specific spectral signatures. This latent space, shown in the center, represents the data in a compressed form. During training, the model learns to differentiate between noise and actual spectral information, ensuring that noise is not retained in the reconstruction process. The decoder reconstructs the hyperspectral band from the learned latent space, now free from noise artifacts. The output seen on the right shows a cleaner and sharper image compared to the noisy input. By implementing the denoising autoencoder, we achieved a significant improvement in PSNR from 14 decibels to 44 decibels, ensuring that the spectral signatures remain intact while suppressing unwanted noise. This enhancement plays a crucial role in improving the accuracy of mineral detection, making hyperspectral data more reliable for geological exploration. Land cover classification is a crucial step in hyperspectral analysis, allowing us to distinguish between different surfaces like vegetation, water, and soil based on their spectral responses. Each land cover type interacts with light differently, which helps in accurate classification. By applying the spectral indices of the land covers, we can systematically classify land cover types, enabling more precise environmental and mineral exploration studies. This graph represents the smooth reflectance curve of these three major land cover types across different wavelengths of the electromagnetic spectrum. Pixel Purity Index helps in identifying spectrally pure pixels, which are essential for accurate mineral classification. These pure pixels represent distinct land cover types without significant spectral mixing, making them ideal for mineral identification. In this visualization, the red highlighted regions indicate the top 10% of PPI pixels, which are the most spectrally pure. To accurately detect hematite in our study area, we use spectral reference data from the USGS Spectral Library. The left image shows hematite in its pure mineral form, while the right graph represents its characteristics spectral reflectance curve derived from the ASCII values in the USGS spectral database. By comparing our hyperspectral data to the hematite reference spectrum, we can confirm the presence of iron-rich deposits in our target region. This reference spectrum serves as the benchmark for spectral matching and classification, enabling precise identification of hematite in our hyperspectral mineral mapping process. Deep learning technique for mineral detection. Clustering plays a vital role in hyperspectral mineral detection, allowing us to group spectrally similar pixels. Traditional clustering methods like K-means or DD-scan often fail to capture complex nonlinear patterns in high-dimensional data. To address this, we employ deep embedded clustering and unsupervised learning method. DEC is a deep learning-based clustering method that transforms high-dimensional hyperspectral data into a low-dimensional latent space before applying clustering techniques. While DEC is powerful, relying solely on spectral information may not be sufficient for mineral detection, as spatial and textural variation also play a crucial role. This brings us to multi-modal DEC, MM-DEC, a fusion-based approach that integrates multiple modalities to improve clustering accuracy. A spectral encoder focuses on pixel-wise reflectance values. Spatial features extracted via a spatial encoder leverages neighborhood information. Texture features derived from a texture extractor captures local contrast and patterns. These three modalities are then fused into a latent feature space, Z, which is then processed using principal component analysis for dimensionality reduction. Finally, the compact feature set is clustered using DEC, and the output is reconstructed into a cluster map highlighting different mineral composition, including our target mineral hematite. By integrating spectral, spatial, and textural features, MM-DEC significantly enhances clustering robustness, leading to a more accurate hyperspectral mineral mapping compared to single modality approaches. Why MM-DEC is a game changer for hyperspectral analysis? More robust clustering, it can handle spectral variability, and it improves mineral detection. Let's talk about each modality in a little brief. The first modality is our multi-modal DEC framework is the spectral encoder designed to extract spectral features from the hyperspectral dataset. This architecture is built using VAE, which enables efficient feature learning and dimensionality reduction while preserving essential spectral information. The second modality in our MM-DEC framework is the spatial encoder, which is responsible for capturing the spatial context of hyperspectral data. Unlike the first modality, which focuses on spectral signatures, this module extracts spatial features, helping to differentiate between land cover types and mineral formations based on their structural patterns. The third modality is the texture extractor using Gray Level Co-occurrence Matrix (GLCM). The hyperspectral data is converted into grayscale or color patterns, which serve as the input for texture computation. The reflectance properties vary across bands, leading to different textures in each band. Texture features such as contrast, homogeneity, energy, and correlation are extracted using the GLCM. GLCM measures how frequently pixel intensity values occur in specific spatial relationship, capturing surface roughness and terrain characteristics. The computations are performed across multiple directional relationships to detect textural variations in different orientations. This step enhances boundary detection, making it easier to differentiate mineral formations from smooth surfaces like soil or water. After extracting spectral, spatial, and texture features from hyperspectral data, the next critical step in MM-DEC framework is the fusion of latent spaces. This fused representation ensures that we integrate complementary information from all three modalities, leading to more robust and accurate clustering results. A cluster map is generated as the output, which highlights the region rich in hematite or other minerals, aiding geological exploration. This cluster map represents the output of MM-DEC framework, where different colors indicate distinct mineralogical and land cover cluster. The yellow highlighted regions correspond to our hypothesized hematite-rich zones, identified based on their unique spectral, spatial, and textural properties. We use cosine similarity, a widely used metric for spectral matching. This approach measures the angle between two spectral vectors, one representing the centroid of a cluster and the other being the reference spectrum of hematite from the USGA spectral library. How do we interpret the cosine similarity? If the theta is closer to 0, it reflects strong similarity. If the theta is closer to 90 degrees, it reflects no relationship. If the theta is close to 120 degrees, it reflects opposite spectral signatures, which suggest an entirely different mineral composition. Using cosine similarity, we achieve the highest accuracy with MM-DEC with 98.69 similarity score as against other compared methods like DEC with residual autoencoders or modality 1 and modality 2 taken alone at a time. Silhouette score. Silhouette score is a metric that measures how well each data point fits within its assigned cluster while maintaining separation from other clusters. It ranges from -1 to 1, which indicates closer to +1, well-clustered points with good separation, closer to 0 overlapping clusters, and negative values signifies misclassified points. With an average silhouette of 0.79, our MM-DEC framework demonstrates excellent clustering performance, ensuring precise mineral classification and robust hyperspectral mineral mapping. Davies-Bouldin Index (DBI). The DBI evaluates how well separated and compact clusters are, ensuring optimal classification of hyperspectral data. It is a widely used metric for assessing the clustering quality. The x-axis represents the number of clusters ranging from 2 to 7, and the y-axis represents the DBI score, where lower values indicate better clustering. The best clustering configuration is highlighted at 4 with a DBI score of 0.29, meaning it achieves the best balance of separation and compactness at k is equals to 4. The low TPI confirms that MM-DEC successfully differentiates hematite-rich zones from other land covers, validating its effectiveness for hyperspectral mineral detection. To conclude, our work presents a novel framework for mineral detection using hyperspectral imagery. The MM-DEC approach leverages deep learning, multimodal fusion, and advanced clustering techniques, setting the stage for future applications in remote sensing and geological exploration. Thank you for watching. The work can positively contribute to the advancement of hyperspectral mineral detection. If you have any questions, feel free to reach out.